Alright guys, we're going to be taking a look at heating curves in this video and how temperature and energy affect the state of matter. This will take a look at something you read about in the book and did in your reading guide, but we're going to go more in depth into what the graphs mean and the calculations involved. So a heating curve. Heat added to a solid will change it from a solid to a liquid to a gas, so changing the state of matter. And when that happens, particular patterns of temperature change are followed during the heating process. So we are going to start to see that as we change any substance from a solid to a liquid to a gas, we're going to get some patterns in the temperature change as the energy is added. A graph of the temperature change versus the heat added is called a heating curve. And you'll notice that it is temperature versus heat. Those two things are often mixed up, but they are not the same thing. So if we looked at our graph for this, we're going to have temperature, which we measure in degrees Celsius on the y-axis, and we are going to have energy on the x-axis. We measure energy in joules or kilojoules. So we're going to be taking a look at those two things and comparing them to each other. Here we can see a beaker of ice at negative 100 degrees Celsius and a graph of the temperature versus heat. So this is its heating curve. The large dot is where our temperature currently is at zero heat being added. So as the flame below the ice gives it heat, our temperature is going to start to rise. And we are going to get our ice to 0 degrees Celsius. So all we've done is heat up the ice to its melting point. We haven't actually begun to melt it yet. If heat is continues to be added, then the ice will turn into liquid. It will go from its solid phase to its liquid phase. During the melting process, the temperature does not change. So at the beginning, we heat the ice to its melting point, and then as it's melting and it's going from that solid to the liquid phase, the temperature is not changing. Now we can see that our beaker has the water at 0 degrees Celsius. It's all become liquid. As we add more energy to the beaker, the water is going to go from 0 degrees Celsius and be heated to 100 degrees Celsius to its boiling point. So as the heat's being added, we're just warming up the liquid. When it reaches 100 degrees Celsius, then the liquid can begin to boil. That is its boiling point. So as we go from liquid to the gas phase, you can see that the beaker completely empties of all the water. So all the water is going from liquid to gas and boiling and evaporating away. During that process of changing from the liquid to the gas, the temperature of the liquid does not change. Our thermometer didn't change its temperature. So that means that at the beginning when we had the flat part and in the middle when we had the flat part, those were both the places where we were changing our state of matter, going from solid to liquid and then liquid to gas. During those phase changes, the temperature of this liquid or of the solid does not change. All of the energy is going into breaking the intermolecular forces between the molecules. The last section of the graph, the last not vertical but tilted section of the graph, shows our gas being heated. So if we could capture the gas that was evaporated from the beaker and hold it in a container and continue to heat it up, then we would see that the gas would change its temperature. It would continue to heat. So we have two different types of sections in this graph. We have sections where temperature is increasing and where temperature is staying constant, the horizontal sections. So we have heat being constantly added to our liquid, but during the flat sections where we have the phase change, the temperature stays constant. So these heating curves have some different sections, and we have to be able to see what's going on in each section. What we are going to focus on are the two flat sections where we're changing from solid to liquid and liquid to gas, where we're doing a change in the state of matter. We're going to look at the calculations done for those sections of the graph. At the molecular level, so heating curves are going to describe how heat added to a substance relates to the temperature and phases of the substance, as we've seen. So we can take a look at the graph given here and see that we start out with our solid phase. We have the melting phase where we're taking our solid and changing it into a liquid, and temperature does not change, it stays constant. Then we heat that liquid to its boiling point, and then we boil or vaporize the substance, change it into a gas, and again the temperature doesn't change, and then we can heat the gas that's formed. We can also look at this in reverse and go the other way and think about it, the gas condensing into a liquid, the liquid cooling, and then the liquid freezing into a solid, and the solid being cooled to a lower temperature. So while one phase changes to another, the temperature remains constant as the heat energy is used to break bonds. So during our two phase changes on the graph, the energy that's going in is being used to break the bonds, the intermolecular forces between the particles, or to form them in the case of condensation and freezing. When the temperature changes, so during the other parts on the graph, when our temperature is actually changing during the solid, liquid, and gas phases, the energy is being used to make the particles increase their kinetic energy or move faster. So we're just trying to shake those particles around, get them to move faster, and heat them up, because that's what temperature actually measures. So the heat of fusion. Heat of fusion, or H with the subscript FUS for fusion, is the amount of energy or heat required to change 1 gram of a substance from a solid to a liquid, or from a liquid to a solid. So going from solid to liquid, we're adding energy in, endothermic. Liquid to solid, we're getting rid of energy, so it's exothermic. Every chemical has different values for the heat of fusion. They're experimentally determined and can be looked up in any reference. So heat of fusion, the word fusion talks about fusing or putting things together, so that often refers to the freezing part, and we just use the same numbers for the opposite. For the melting part, we just see how the temperature change is different. We can use a substance's heat of fusion to determine how much energy is needed, so the positive, to melt a specific mass of the substance, or how much energy is given off, negative, when the substance freezes. So we want to pay attention to the wording of the questions to see if our answer needs to be negative or positive based on the situation and what's happening to the substance. So the numbers won't necessarily be negative or positive. We have to make them negative or positive to reflect the direction of the heat flow. So we have our equation here, Q equals M times the heat of fusion. So Q represents our heat, and that's a heat gained or lost in this situation, and M represents our mass of the substance. Our units for our heat of fusion can be given in joules or kilograms, joules or kilojoules per gram. So it's going to be a mixed unit. And then our mass is given in grams. This will allow our Q, our energy or heat, to end up in joules or kilojoules. So we're going to take a look at an example of calculating this. So it says how much energy is gained if a 22.3 gram piece of ice at 0 degrees Celsius melts completely into liquid water. And it gives us the heat of fusion for water is 335 joules per gram. So we've got a couple things. We are given 22.3 grams. It tells us it's at 0 degrees Celsius. So we are already at the freezing point of water, or the melting point of water. And it gives us the heat of fusion for water. And what it asks us to find is how much energy is gained. We're gaining energy. That means it's going to be positive. So we're going to use our equation, Q equals m times heat of fusion, and simply plug in our numbers. So our energy, Q, equals our mass, so 22.3 grams, times our heat of fusion, 335 joules per gram. And we just need to multiply our numbers together. So 22.3 times 335. And I end up with 470.5. Our units here, we can see the grams times the grams will cancel out, so we are left with joules of energy. And then, of course, our fun and favorite final step is to check our significant figures, your favorite part. So we have 3 significant figures in our grams and 3 in our heat of fusion. So we want 3 in our answer, 747. Now remembering back to our first unit, we do not just drop the rest of the number. The 7 stays the same because the next digit is 0. So we want to keep the value 7,470. We just drop the 0.5. The 0 at the end will not count since there is no decimal, so it's not significant. And our answer is in joules. So it's a simple heat of fusion equation. Now, it did say that our energy is gained. We are adding it, so we want to leave this as a positive number. All right, we're going to take a look at another example. So it says how much energy, so we're looking for energy in kilojoules, so we're going to pay attention to that part, is released when 46.0 grams of ethanol is frozen. We have the heat of fusion of ethanol is 108.9 joules per gram. So it does ask for our answer in a different unit, so we can take care of that at the end. We want to get our joules into kilojoules, a little bit different. But we're going to have the same approach. So we're going to start with Q equals the mass times our heat of fusion. Our heat of fusion is for ethanol, so we're looking at a different chemical here. So our energy equals our mass, 46.0 grams, times our heat of fusion. So 108.9 joules per gram. So quickly I'm going to do the calculation. 46 times 108.9. I get, change my color here, 5009.4. We can see our grams will cancel, so we're left with joules. And we're going to take a look at our significant figures. We've got 3 in our mass and 4 in our heat of fusion. So we want to round to 3 digits. So we have 500. We check the next digit. So the 9 will round the 0 up. So we get 501. And then we want to make sure that our digits are in the correct place. So our 5 in the first answer is in the thousands place, so we need to add another 0 to our answer to keep the 5 in the thousands place. That 0 at the end won't count because there's no decimal, and that is in joules. Now, our answer does ask for it to be in kilojoules. So there are 1,000 joules in a kilojoule. I'm going to do the conversion right here. Take this, do a little table. 1,000 joules in 1 kilojoule. So we just want to divide it by 1,000, and that will give us 5.01 kilojoules. There's our final answer. One last thing we do want to check for is, does it need to be positive or negative? So we are freezing this, and the energy is being released. So those are two clues for us. So the energy is going out, meaning it's a negative value. It's exothermic. So we want to make sure our Q, our answer, is negative. So Q equals negative 5.01 kilojoules. All right, now we're going to take a look at heat of vaporization. It's a very similar concept. Not much is different here, just the different states of matter. So heat of vaporization, or H with subscript vape, is the amount of energy or heat required to change 1 gram of a substance from a liquid to a gas, or from a gas to a liquid. So going from liquid to gas, that's our endothermic process. We're taking in energy to boil something. And going from gas to liquid, it is going to be exothermic. We're going to give off the energy. Every chemical has different values for heat of vaporization, just like the heat of fusion, and we would look those up in a table. We can use a substance's heat of vaporization to determine how much energy is needed, being the positive, to boil a specific mass of the substance, or how much energy is given off, it's negative, when a substance condenses. So we have boiling, changing it from liquid to gas, and condensing, gas to liquid. That seems to be the one everybody forgets, is what condensing is called. So our equation, you'll notice, is exactly the same. We just are using heat of vaporization as opposed to heat of fusion. So Q is still our heat gained or lost, M is our mass, and our units can still be joules or kilojoules per gram. All right, we have one last example to look at. So we're going to look at how much energy is given off. So we are giving off energy. That means it's exothermic. It's going to be negative for this one. When 10 grams of steam at 100 degrees Celsius condenses into liquid water. And our heat of vaporization of water is 2,330 joules per gram. So our equation, Q equals M times our heat of vaporization. We're going to simply plug in our numbers. Our heat equals our mass, 10.0 grams, times our heat of vaporization, 2,330 joules per gram. We can see that our grams will be multiplied and cancel out. All right, so our answer is going to end up being Q equals 23,300, and our units are going to be joules. Now let's take a look at our significant figures. Since we have the decimal in our 10.0, all 3 of those digits will count. So we have 3 significant figures there, and we have 3 significant figures in our heat of vaporization. So we want 3 in our answer. So if we look at this, the zeros at the end do not count on our 23,000 in our answer, 23,300, because there's no decimal at the end. So we already have 3 significant figures. So we can leave our answer as is. But the one thing we want to do is go ahead and make it our answer negative, because it's an exothermic process. We are giving off that energy. We want to make it negative. So these are some simple calculations that we can do, and all this does is tell us how much energy it either takes or how much energy is given off when something is changing from a solid to liquid or liquid to gas, or the other way around. And so it's telling us the amount of energy that has to be put in, or how much energy is released when we're changing and either breaking or forming the intermolecular forces. Sorry, that was really wordy. So for example, if we took a piece of ice and we melted it, we could calculate now how much energy it took to actually break down its intermolecular forces. And that's all this is showing us. So make sure you got your notes down, wrote down all your examples so you have them to refer to, and we'll see you in class.